Okay, let's go ahead and get started. Uh, Today we're talking about gases, and I sent out the original script for the gas problem sheet, but we're going to be probably working a lot more than what's on this paper. I'll try to keep everything one page. First up, there's a quick PowerPoint to go through. It kind of gives a little background about gases, and it's entitled All About Gases. Gases have variable shape and volume. Gases expand uniformly. Gases compress uniformly. Gases have very low density. 1,000 times, water's 1,000 times more dense than air. Gases mix uniformly with gases in the same container. There's three main variables in gases when you start talking about gases. There's pressure. Pressure is defined as a force divided by some area. Temperature, for any gas law problem that we'll use temperature. Temperature must be in Kelvin. And the volume is usually expressed in liters, but not always. Sometimes milliliters are used too. But generally speaking, the most common unit for volume is liters in gas problems. Atmospheric pressure, there's pressure acting on you at all times from gases. Again, if molecules collide more often, pressure increases. If molecules collide with more energy, pressure increases. Some units of pressure. The most common one is what's called an atmosphere, or ATM. There's also inches of mercury, millimeters of mercury, torr, and PSI, pounds per square inch, which is a very common one. If you've used any athletic equipment such as soccer balls, basketballs, footballs, they're usually rated as a PSI, pounds per square inch. Also, any automobile tires, tires in general, pretty much any vehicle would be rated in what's called PSI. And KPA is kilopascals. That's mainly for science and engineering folks that use KPA. Variables affecting gas pressure. Well, if you increase the volume of the container, you decrease the pressure. If you decrease the volume of the container, you increase the pressure. It's just like squeezing a ball. Pressure and volume are inversely related. As pressure goes up, volume goes down. And as pressure goes down, volume will go up. Temperature. Temperature is also a player in this. There's temperature increases, pressure increases. That's a direct relationship. Number of moles can be a player in this, especially when we get to the ideal gas law. As moles increase, pressure increases. As moles decrease, pressure decreases. There's Boyle's law. Boyle's law is just a direct relationship between P1 V1 and P2 V2, and what that means is, as we'll see when we get to the gas law problems, that if you have a 4-variable gas law problem, you have to have 3 numbers there, and you'd solve for either the P2 or the V2. Charles' law introduces temperature. Volume's proportional to temperature at some constant. It's V1 over T1 equals V2 over T2. Again, any gas law problem, the temperature must be in Kelvin, and the conversion between Kelvin and Celsius. You take the Celsius temperature and you add 273 for it, and then you get the number in Kelvin. Lusak's law, pressure over temperature. Basically, P1 over T1 equals P2 over T2. And again, volume there remains constant. And then there's Avogadro's law. If you introduce moles, V1 over N1, V2 over N2, volume and mole relationship. It's not a very common gas law problem there. The combined gas law is what we'll be focusing on in the first half of this. And that's a 6-variable expression. There's P1, V1, T1, which is what I call set conditions 1. And there's P2, V2, T2, which is what I call set conditions 2. That's Boyle's, Charles, and Lusak's law all combined together. A little bit on vapor pressure. Vapor pressure is the gas pressure that exists above a liquid. So liquids with low vapor pressures have high boiling points, and liquids with high vapor pressures have low boiling points. And there's water at 100 degrees C and diethyl ether at 34.6 degrees C. Dalton's law of partial pressures. Basically, if you know the pressures of the individual gases, you can add them up to the total pressure. And if you've ever been scuba diving, that's how they blend the gases. They mix the gases by pressure in the tanks. There's kinetic molecular theory of gases. Just tells you a little more about what's inside a gas. Gases are very tiny molecules. Gas molecules are very rapid motion, move in straight lines and travel in random directions. Gas molecules have no traction for each other. Gas molecules collide without losing energy. That's what's, if you ever go on and take physics, we'll call that what's called an elastic collision. The average kinetic energy of gas molecules is proportional to the Kelvin temperature. Again, any gas law problem, the temperature must be in Kelvin. And the last gas law we'll look at is the ideal gas law. PV equals nRT. There's pressure, there's volume, the number of moles. R is a gas constant. That's 0.0821 liter atmospheres per mole K. And there's problems on the ideal gas sheet. And that was it for the gas PowerPoint. So we're just going to jump right in and work some problems. Again, we're back on the problem sheet to get us scripted. First up, when you got a combined gas law problem, and this is number one we're looking at. I'm going to fill in the boxes. 25 atmospheres, 55 liters, 102 K, 98 K, and 62 liters. In any combined gas law problem, one of the boxes has to be left open. So you're going to have 6 numbers, but only 5. You're going to end up with 6 numbers, but only 5 will be filled initially because you're going to solve for the 6th. So when you have a combined gas law problem, you start with what I call the root equation. In our first example, we need to find out what the new pressure is given set conditions 1 and set conditions 2. So we need to do some algebra. What we need to do is get P2 by itself. So to get P2 by itself, I've got to move V2 and T2 to the other side. P2 needs to be isolated. So T2 is on the bottom. What I do is I multiply both sides by T2, and I bring T2 to the top on this side, and T2 has now been moved. Next thing I have to do is move V2, which means I need to multiply or divide both sides by V2, and I move that over to the other side. So my new functional equation is T2 P1 V1 over V2 T2. In any combined gas law problem, there's going to be 3 numbers on top and 2 numbers on the bottom. If you do not have that in your final equation, which I call the functional equation here, there's something wrong. So I'm going to bring that equation over. That's going to equal what I want in the box P2. So at this point, what you're doing now is you've got players assigned to the field. You need to put numbers in place of the letters. So first up, T2. T2 is 98K. P1, 25 atmospheres. And V1, 55 liters. V2, 62 liters. And T1, 102K. So now I can check to make sure I end up with pressure at set condition 2 in atmospheres, which means when I do the nexus or the connection, everything should cancel out except atmospheres. So let's see what we got. We got K cancels with K, and liters cancels with liters, and the last unit standing is atmospheres. So the knockout for this one is 98 times 25 times 55 divided by 62 times 102. So at this point, you execute it. 98 times 55 times 62 times. I came out with 21.30771. Probably way more figures than I need. And I do my sig fig check. I've got 2 here, 2 here, 3 there, 2 there, 2 there. So my answer is going to have 2. So that's going to be my round spot. So I'm going to go with 21. So I place 21 as my new pressure, given set conditions 1 and set conditions 2. And we've just worked our first gas law problem, which was a P2 problem. So let's try another one here. I think I have 2 rounds on that. This is number 2. Number 2, I have 250 atmospheres, 390, 310, 510. Notice all temperatures are in Kelvin. 560K. And the box that's missing is V2. So I go back to my root equation. In this case, the player I need to isolate is V2. So I'm going to move T2 just like I did last time, downstairs. I'm going to multiply that so it cancels. So I multiply both sides by T2, so it's upstairs on the other side. So T2 is gone. And if P2 is upstairs, I need to move it downstairs on the other side. And there's my functional equation, T2 P1 V1 over P2 T1. Notice 1, 2, 3 on top, 1, 2 on the bottom. So I have my equation now. It lets me solve this problem. So now I just plug the numbers into the letters. T2 is 560. P1 is 250. V1, 310. P2, 390. And T1, 510. And again, I'm going to check the nexus to make sure that we're left with a volume which should be in liters. So let's see, K cancels and atmospheres cancels, and we are left with liters. So the knockout for this, 560 times 250 times 310 divided by 390 times 510. Again, 3 on top, 2 on the bottom, just like a gram to gram problem. And I got 218.200. I know that's way more figures than I need. So do my sig fig check. 2, 2, 2, 2, 2, 1, 2. There's my round spot. So from 218, I'm going to go up to 220. Give me 2 sig figs, and I'm good to go. That is a V2 problem. Number 3. It's 425, 625, 125, 175, 125, and it's a T2 problem. So I go back to my root equation. T2. This is what I want, but it's on the bottom. So what I'm going to do is put it on the top. I put it on the top by flipping everything over. So if I flip everything over, I have T1 over P1 V1, which is equal to T2 over P2 V2. Then I'm going to move this P2 V2 in one step. So it's downstairs. To make a long story short, it's going to go upstairs. And then my functional equation for this problem is going to be P2 V2 times T1 over P1 V1. So I'm going to bring that over here. And there I go. 3 on top, 2 on the bottom. Now I'm just going to put the numbers in for the letters. P2 is going to be 625. V2, 175. T1, 125. That. I haven't used V1 yet. 125. P1, I'm sorry. 425. Ahead of myself here. Conclusion. And V1 is going to be 125. And if we're connected right, we should be left with a temperature in Kelvin. So let's see here. Atmospheres goes. Liters goes. I got 2 liters here. What's going on? V2 is 175, and this should be T1, which should be in Kelvin. 125 K. So what I've got now, I've got my 5 numbers, and I'm left with K. So I'm going to have 625 times 175 times 125 over 425 times 125. Essentially, the 125s are going to cancel out. I'm going to be left with 625, 175 times, and 425 divide. And I come out with 257.3529. Check my sig figs. 3, 3, 3, 3, 1, 2, 3. There's my round spot. No reason to change anything. I'm going to go ahead and put 257K into my T2 box. Okay, let's see here. Number 3, number 4. We are back to a P2 problem. Let's see, 360, 520, 98, 820, 65. So, back to our root equation. I need to isolate P2 by itself. So, if V2 is upstairs, it goes downstairs. And if T2 is downstairs, it goes upstairs. And there you have the functional equation. So the equation for this one, T2 P1 V1 over V2 T1 equals P2. So let's start. We got T2, 65K, P1, 360, V1, 520, V2, 820, and T1, 98K. And if everything cancels out correctly, there should be only atmospheres left. So Kelvin goes and liters go, and we're left with ATM. So the knockout for this one, 65 times 360 times 520 divided by 820 times 98. 65 there, 360 times 520 and come out with 151.4186. Sig fig check 2, 2, 2, 2, 2. Everything's 2. So there's my spot. I'm going to go with 150 atmospheres, and that will give me my 2 sig figs. That is number 4. So let's take a look at number 5. Got let's see, 525, 925, 725, 102, 10. So it's a V2 problem. So V2 must be isolated. T2 is downstairs. T2 will go upstairs. T2's gone. P2 is upstairs. It must go downstairs in the new order. So the new order is T2, P1, V1 over P2, T1, which is equal to V2. So now we substitute T2, 109K, P1, 525 atmospheres, and V1, 725 liters, P2, 925 atmospheres, and T1, 102K. So if all works out the way it should, we should be left with liters. Let's see here. K cancels, atmospheres cancel, and we're left with liters. So we've got the knockout here. It's going to be 109 times 525 times 725 divided by 925 times 102. 3 on top, 2 on the bottom. I come out with a raw answer of 439.7257. I do my sig fig check. 3, 3, 3, 3, 3. 1, 2, 3. I'm going to round that up to 440. And I'm going to stick a point in there to give me my 3 sig figs. That is V2. So next up, is number 6. Got 99. I've got 65. I've got 25. I've got 75 and 28. So we're looking at a T2 problem. What I want is on the bottom, so what I'm going to do is flip this whole thing over. I have my T's on top. Downstairs, upstairs. And now we have the equation we want. P2, V2, T1 over P1, V1 is equal to T2. Let's see here. Let's execute P2, P2, V2, T1, P1, V1, and let's check our nexus here. We've got atmospheres gone, we've got liters gone, we are indeed in K. So our knockout for this one is going to be 65 times 75 times 28 divided by 99 times 25. And let's see what we got. And I come out with 55.15151. Right. Sig fig check. 2, 2, 2, 2, 2. 1, 2. No reason to change anything. I'm just going to slide that double 5 right into that box. And that is our first round of combined gas law problems. In this next step, we're shifting gears. We're going to what's called the ideal gas law. The ideal gas law PV equals nRT, pressure, volume, number of moles, gas constant, and temperature. And here it's 5 numbers. You must always have 4. And this one is a constant. So each box will always be filled with the number for R, which is 0.0821. And we're either solving for pressure, volume, moles, or temperature, respectively. So let's see what we got for the first one under ideal gas law. Take a look here. $75 liters. We are solving for P of the PV equals nRT equation. We've got V, we've got N, we've got R, we've got T. Now we've got to get V by itself. To get V or P by itself, so V is upstairs. So upstairs goes downstairs. So there's our equation. So we've got N first up, 62 mole. We've got R, and that's liter atmospheres over mole Kelvin. And we've got temperatures 28 K. And downstairs, we have the volume of 75 liters. So I've used all my 4 numbers there. And if the cancellation in the nexus is correct, we should end up with atmospheres in the pressure box. So we got moles gone, we've got liters gone, and we've got Kelvin gone. And that's the last unit standing, is atmospheres.
What did you do the L times ATM for?
That's the units on the gas constant.
That's T?
That's liters times atmospheres over moles times Kelvin. That's the units for R. If I want to put them in the box, which I don't always do, liter atmospheres over mole Kelvin. Just the units of R. So we can track the units, and like I said, there should be 1 unit left when we do all our cancellation. So the knockout here is going to be 62 times 0.0821 times 28 divided by 75. I come out with a raw answer of 1.9000341. Now I'm going to do my sig fig check. 2, 2, 2. There's my round spot. No reason to change anything. I'm going to slide 1.9 into the top box. And that is the first of our gas law problems. Again, we're going to do a tree, what I call a tree. We run down the tree. V2 will be next. V would be at next. Thinking combined gas law here. N next, and then to finish up, we'll do a round with T. So we will run the full ideal gas law tree here. So let's see, next up, number 8. Always need 5 when you're doing an ideal gas law problem. 125 atmospheres, blank, 222 mole, R, and 398. So we need V by itself, P is upstairs, P is going to go downstairs. So now we're ready to plug in. N, first up, 222 mole. R, 0.0821, again, liters, atmospheres, mole, Kelvin. And T, 398 K. And P, 125 atmospheres. That twice, 222, enter 0.0821 times 125 divide once, not twice. 58.03, bunch of 2s. I'm gonna need them anyways. 3 sig figs, 1, 2, 3, 1, 2, 3, 1, 2, 3, 3 sig figs. There's my round spot, no reason to bump that up. I'm going to go with 58.0, and if all is correct, I should have just liters standing. Well, let's see, mole goes, atmospheres goes, Kelvin goes, and the last standing is liters. So we know we're correct. Nine. 62 atmospheres, 25 liters, it's blank, 69 K. Solving for N. If you get N by itself, well, RT is upstairs, RT goes downstairs. So there's our equation. Let's see, first up is P, 62 atmospheres. V, 25 liters. R, 0.0821 liter atmosphere, mole Kelvin, and T is 69 K. So our execution here is going to be 62 times 25 divided by 0.0821 times 69. And if we are correct, we should be left with moles. Let's see, atmospheres goes, liters goes, Kelvin goes, and there's the last player standing, mole. So 62 or 25 times 0.021. 69 times 5. And I come out with my raw answer of 273.6147. It's like two sig figs. So there's my round spot. So I'm going to go and round down to 270 moles to get my 2 sig figs. That is number 9. And number 10. Number 10. Another tree. 5 branches. Let's go number 25. 262. 325. 0.0821. And the T box is empty. Need to get T by itself, NR's upstairs, NR downstairs. So there's our equation, PV over NR is equal to T. So 125 for P. V is 262. N is 325. R 0.0821 liter atmospheres mole Kelvin. So our knockout 125 times 262 over 325 times 0.0821. And if all ends correctly, we should be with a temperature of Kelvin when we end this game. So let's execute this. Okay, I'm going to leave this one in side note. 1.227, it's probably more than I need, times 10 to the third. Do my sig fig check. I've got 3, 3, 3, 1, 2, 3. There's my round spot. I'm going to round that 2 up to a 3. 1.23 times 10 to the third Kelvin. And that's our first round of gas laws. In the next round, I'm just going to make up the numbers. We're going to go back and just do another cycle of the whole system. So, let's see. I'm going to go 4 sig figs on this one. This next one's going to be a P2 problem. Here's set conditions 1. Here's what I have as set conditions 2. Set 1, set 2, and I need to go after P2. So everything always starts with the root equation. In this case, I need P2 by itself, T2 downstairs, T2 goes upstairs, V2 upstairs, V2 goes downstairs. 3 on top, 2 on the bottom. There's our functional equation. Here's our number board. So let's start with T2, 1907K. P2 comes off the board. Next up, P1, 6231 atmospheres. Next up, V1, 5251 liters. V2, 4821 liters. And let's see, we are left with T1, which is 1302K. Okay, if everything came out, we should have atmospheres left. First, we'll check. We've got 1, 2, 3 on top, we know is right. 2 on the bottom. And then our knockout for this is going to be 1907 times 6231 times 5251 divided by 4821 times 1302. I'm going to be dealing with some big numbers here. 6231, 5251. I came up with a raw answer of 9.94035 times 10 to the third. I'm going to do my nexus check. Next, Kelvin gone, liters gone. I'm indeed with atmospheres. That's what I want. Next is my sig fig check. 4, 4, 4, 4, 4. Round spot, 1, 2, 3, 4. There's my round spot. No reason to change anything, so I'm going to transfer that number over to the little board here. 9.940 times 10 to the third atmospheres. That's a P2 problem. I said we're going to run the tree here. Another round of combined problems. So let's do this out. this is going to be a V2 problem. So everything starts with the root. You get V2 by itself, T2 upstairs, T2 downstairs, T2 upstairs, P2 upstairs, P2 downstairs. That right there is really the hardest part of working a gas law problem. Because then all you're doing next is taking the numbers, sticking them in for the letters, and making sure you only use them once. So T2 up. P1. V1. P2. And T1. And there we have it. And if all ends well, we should be in liters here on the big board. Let's execute it. 834 times 623 times 931 divided by 587 times 629. So 834 623 times 623 came out with 1.310, 131 times 10 to the third as the raw. We're going to do the nexus check next. Let's see, Kelvin gone, atmosphere's gone, liters left standing. I've got that part good. I've got 1, 2, 3 on top, 2 on the bottom. That's good. I've got sig fig check, 3, 3, 3, 3, 3. I need 3. 1.31. Use that as my round. Right here is the round spot. Not going to change anything. 131 times 10 to the third liters. Next we're up with T2. Let's see here. Let's do 2 sig figs. Spheres. 25 spheres. 37 liters. 22 liters. 15K. It is a T2 problem. The T2 box is empty. So I'm going to start with my root. Well, I got my temperatures downstairs, so I'm going to go ahead and flip that. So that's going to be my starting equation. P2, V2 downstairs, P2, V2 upstairs. Now I have my functional equation. 1, 2, 3 on top, 2 on the bottom. And now I call this the plug-in phase. We take the numbers and plug them in. P2, 25 atmospheres. V2, 22 liters. T1, 15K. P1, 83 liters, 83 atmospheres. Units, right? And V1, 37 liters. One thing, I checked my big board. I've got all my numbers X'd out, so I know I've used them. And then I cross them out here in my variables. So my knockout is going to be 25 times 2, 20, 22. That's L. 15 over 83 times 37. 3 on top, 2 on the bottom. We execute. I came out with 2.686421. I'm going to double check that one. $2.68421. Yes, double checked it. Sig fig check. 2, 2, 2, 2, 2. Everything's 2. There's a round spot. I'm going to round up to 2.7. I'm going to do my nexus check. Atmosphere's gone, liters gone, K gone. And I can just slide that number right into the K box. That's 2.7. That is another round of combined gas law problems. So let's run another tree on the ideal gas law. Okay. Ideal gas law. Again, we're doing another round of ideal. PV equals T. We need P by itself. V's upstairs, T's downstairs. So there's the actual equation we're going to use. Now we plug in 92. R. Yeah, once you get this down, you don't have to stick R in because you know the units are going to cancel out because it's going to be assembled correctly. 63K. And V is 25 liters. Since we talked units, let's check the nexus. Liters are gone, moles gone, Kelvin's gone, and we are left with ATM. So the knockout here, 92 times 0.0821 times 63 divided by 25. 92, enter, 0.0821 times 63 times 25, divide. I come out with a raw answer of 19.03406. My sig fig check, deuce, a deuce, a deuce. There's my round spot, no reason to change anything. I'm going to slide that 19 atmospheres right in there. And call that one. Let's see, that was a P. Use 3 this time. So this time it's going to be a V problem. So P, T, V. So I need to get V by itself. P's upstairs, P downstairs. So let's take a look at what we got. 127, N, 602. Do this in the right order. R, and T, and P. Right, so the knockout is going to be 602 times 0.0821 times 525 divided by 127. And I came out with a raw answer of 204.3126. Sig fig check next. 333. There's my round spot. I'm not going to change anything. I'm going to slide the 204 in there. Do the nexus check. Atmosphere's gone. K gone. Mole gone. And it looks like I'm left with liters, and it played out just perfect. So next up, we're going to do an N problem. So we're going to slide down the tree here. Back to 3. 6. So let's see, we've got an N problem. PV equals, and going to get N by itself, RT upstairs, RT downstairs. So PV over RT equals N. So P is 928. V is 526. R and T. So let's execute. I'm going to leave this one in side note, so it's big. 4.6449 times 10 to the fourth. I say big check 333, everything's 3. So that's my round spot. I'm going to go with 4.64 times 10 to the fourth mole. I can do my nexus check. Atmosphere is good, liter's good, Kelvin good, and mole's the last player standing. So, let's slide down. Key problem. So PV T, let's go back to 2, 22 atmospheres, 9, 4. Right, there we go. T. So I've got to get T by itself. So NR's upstairs, NR's downstairs. There it is. So let's do P22. B 69. N 84. And R 22 times 69 divided by 84 times 0.0821. Now we execute 22 enter, 69 times 22 enter, 69 times. I came out with 220.1148. This looks like it's going to be 2, 2, 2. The deuce on sig figs. There's my round spot. No reason to change anything. I'm going to slide that right in there. And I can do my nexus check. Should come out with K. Atmosphere is gone. Liters gone. Mole gone. And we are left with K. that's gas loss. Is there any one in particular you want to see again? Anybody? That's gas laws. That's pretty much all we do with them. That is gas laws. Today, I will get another take-home set. I call it a take-home set, but it's a practice set of problems out today, which will be chem calcs and a round of gas loss. Then next Tuesday, we've got our last topic, which is molarity. So is there any questions? Any questions? Any questions? Any questions? Everybody got their exam 3 in. Exam 3 was put to bed. Hopefully there was no problems there. Took care of all that. Like I said, exam 4 will be ready to go out a week from tomorrow. So is there any questions? Any questions? Anybody? Anybody?
Nope, I'm all set.
Oh, what was that, Jade?
I said I'm all set.
Okay, excellent. Well, if there's nothing else, that's pretty much it. Like I said, I'll have a practice set going out today and the update. And like I said, we're right on track to pretty much start wrapping things up next week. Another round of chem calcs, molarity, and that's pretty much it. Okay. So if there's no other questions, I'll go ahead and end the meeting, and I'll get this link out for anybody that wants to watch it again. It'll be up today. So everybody take care, and I will see you next Tuesday.
Thank you.
You're welcome.